Good morning everybody. Friends, we are back here with rate processes. So, in our last lecture, in our last class, we discussed electron transfer in electrodes. So, so electron transfer in electrodes. Okay, so there we talked about the interface of electrode and solution. So interface is talked about interface and interface between electrode and solution. We discussed Helmholtz double layer, Gauss-Chapman layer, and finally we discussed Stern layer, which is a mixture of these two. We also talked about interfacial potential, then connection between galvanic and electrode potential, rate of charge transfer. Then we discussed also the free energy of activation, that is electron transfer. When it is the case of electron transfer reaction, it must be associated with some free energy of activation. So we discussed on that also. We came up with this Butler-Volmer equation. Then you discussed overpotential. And these things we discussed. So today, and also general arrangement of this rate measurements. We general experimental arrangement means how to measure this rate of electron transfer at the electrode. So those we discussed in our last lecture. So today we will start with another topic which is very important in connection with kinetics at electrodes. So it is voltammetry. VOLTAM. Okay, it's the voltammetry. So in this case, current is monitored as the potential of electrode is changed. Now, chronopotentiometry is potential. In that case, potential is monitored as the current density is altered. Now, in this case, what is the use of this voltammetry? This may be used to identify the species which are present in the solution. So it's a electrochemical means of identifying chemical species present in the solution. And of course, when it is the question of chemistry, the most important aspect is the determination of concentration. So using voltammetry you can also find out concentration. Electrodes, like there are various kinds of electrodes, like non-polarizable electrodes. Their potential only slightly changes when a current passes through them, as for example calomel, standard hydrogen electrode, H2PT. And polarizable electrode, those which strongly current dependent, having potential which is having strongly dependent on on current. So the criteria of low polarizability is high exchange current density due to J is equal to J0 into F times eta. Anyway, so voltammetry is one of the techniques which electrochemists employ to investigate electrolysis mechanism. There are numerous forms. So, one is like potential step, another is linear sweep, voltammetry, and third is your cyclic voltammetry. Okay. Now, for each of these cases a voltage or a series of voltage. So, voltage or a series of voltages are applied to the electrode, and the corresponding current that flows is monitored. So, voltages applied to the electrode and corresponding current that flows is monitored. Okay. Now, so current is monitored. Okay. Now, electrodes generally, since you measure, you apply some voltage and you measure current. So, naturally question comes essential elements that are used. So, essential elements required. One is your electrode. Of course, you need electrode generally made up of inert metal, made up of inert metals like gold, AU, PT, not silver. Solvent, generally solvents of high dielectric constant, like your water, acetonitrile, these are used because this will enable your electrolytes to dissolve and help passage of current. So, this helps dissolution of electrolytes, and naturally which is required for the passage of current and generally a background electrolyte, background electrolyte is needed, maybe like NaCl, which are generally electrochemically inert are like NaCl, then tetrabutyl TBAP, tetrabutyl ammonium perchlorate, tetrabutyl ammonium perchlorate. These are generally used, and of course, it is generally added in high concentration of the order of say 0.1 molar. Okay. So, this will allow initially the current to pass through. Okay. And your reactant, your reactive material, the substance on which you will carry out your experiment, apart from this background electrolyte, that is used in low concentration, maybe in millimolar concentration, millimolar, that is 10 to the power minus 3 molar. Okay, so these are the essential elements used. Now in your potential step voltammetry. So first one, potential step voltammetry. Okay, so potential step voltammetry, this applied voltage is suddenly and instantaneously jumped, from one value to another, like say from V1 to V2, and the resultant current is measured as a function of time. Okay, suddenly it is jumped, instantaneously it is jumped, and then the resulting current is monitored as a function of time. Okay, so it is basically a step potential function you are applying. So basically, say from this is this V1, say this is your V2. What you do, instantaneously it is jumped, so from here to here. Okay, and this is time, and this is your voltage. Okay, and you measure the current as a function of time. Like initially it was like this, the moment it is high, then current is high, and then slowly decays to some value maybe. Okay, so and what is happening that and ultimately if you monitor and concentration versus distance, if you plot as a function of distance, if you plot concentration of, say, if you suppose you have a reaction, say m n plus to say m n minus 1 plus. So this reaction, what is happening, you can find out the concentration from the distance. So with distance, I mean this is your distance d, and this is your concentration of, say, m n plus as a function of time. If you plot, what is happening, that maybe it becomes something like this. Okay, so this is your at different times, t increasing. Okay, and this is your bulk concentration, and this is a distance d from the electrode. Okay, so this will give you the idea of how this concentration is changing, and other like this may be ultimately related to your rate of electron transfer. Okay, so this is one way of usually the voltage range is set such that your reduction of m n plus, okay, m n plus to m n minus 1 plus is thermodynamically unfavorable. Okay, and the second voltage, I mean initial voltage V1 is set such that this is not happening, and the second voltage is selected so that the ions which are very close to the electrode, okay, electrode is converted to the corresponding this form. Okay, so current response, this is the corresponding current response. Okay, so what is happening, that current therefore, since you change voltage from V1 to V2, okay, your current response, I mean when the time is very small, I mean there is a huge change in concentration. Okay, there is a huge change in concentration due to this reduction. Okay, those ions which are very close to the electrode, they are affected. That is why there is a huge change in current, and then slowly it decays to your starting value. Okay, the current rises instantaneously after the change in voltage and then begins to drop as a function of time. You see, it is as a function of time. This occurs since the instant before the voltage step, the surface of the electrode is completely covered with reactant. Okay, this is your electrode. Okay, when it is at V1, there was no reaction like this. So, it is completely covered with your Mn plus. Okay, this throughout the solution it has got a constant composition. So, this is your electrode and this is the distance from the electrode. So, composition is almost close. Okay, and once the step occurs, okay, what is happening that this reaction happens, I mean this reaction occurs, and a large current, since this reaction occurs, electrons are required to reduce. So, large current is flowing, that is why it is hugely up. Okay. The first layer of this metal is depleted. So, what is happening that next layer of reactants should come through diffusion close to the electrode, and then reaction will take place. Okay. So, and the reaction to continue, it is there is a need for the supply of the fresh reactant. Okay. And therefore, this happens in this happens due to diffusion, therefore, it requires time. Okay. So, the supply of fresh unconverted metal to the surface and depends upon the diffusional flask, and at short time the diffusion flask is high as the current as the change in concentration between the bulk value and the surface occurs over means at shorter time the diffusion flask of this metal, this metal is high. Okay, as the change in concentration between the bulk value and that at the surface occurs over a short distance. Okay, as the electrolysis in this way, as the electrolysis continues, the material can diffuse farther from electrode, and therefore, concentration gradient is is dropped. Okay. As concentration gradient drops, so the supply of fresh reactant to to surface, and therefore, the current also decreases. Since longer time is given, you see that this is the initially there was a huge concentration gradient, as the distance is more, so distance is more, so it is bulk. So, gradually what is happening that this concentration gradient it becomes like having a fixed value, concentration versus distance. Okay. Therefore, your current as time is increased, concentration gradient is decreased. Okay. So, from this diffusion coefficient can be obtained using some standard relation. You can find out the diffusion coefficient for the ion to the electrode. Okay. So, this is called your potential step voltammetry. This is basically you change the potential, and the moment you change the potential, the ions which are close, they are initially consumed, and then next layer of electrodes ions will diffuse. Okay. So, this diffusion will continue. Okay. At shorter time this concentration gradient was large, but as you give more time, then diffusion occurs, as a result of which this concentration gradient decreases, okay, with time. Okay. So, this happens with this potential step voltammetry. Okay. Now, next thing we were talking about the another point that we should mention, that the concentration polarization. Now, this is your one thing. Another point which we must think of is your concentration polarization. Here we should look into. Now, when the current density is less, the conversion of electroactive species is negligible, but at high current density the consumption of electroactive species close to the electrode results in concentration gradient, as I told you that here this is consumed. Okay. So, therefore, there is a huge concentration gradient which is there, okay, when current density is quite high, and so this results in concentration polarization, that is, the consumption of electroactive species close to the electrode results in a concentration gradient, and diffusion of species towards electrode from the bulk may become the rate limiting process. Okay. As I told you that in potential step voltammetry, this I told you that at the very start of your stepping of voltage, what is happening, that here it is consumed, all the ions close to this is consumed, okay, and then it starts to diffuse. So, it is not that instantly the other the ions which were at a further distance from the electrode, at a further position from the electrode, that will come instantly, it will require some time, okay, and that is diffusion limited, and that is why using some standard relation like current has got some using some equation, that is mass transport equation, and that has relation to your current that is observed. So, you can find out the diffusion coefficient. So, anyway, therefore, a large over potential is needed to produce a given current. In this case, since there is a concentration difference, there is a huge concentration gradient that is created. Okay. Now, polarization. So, therefore, a large over potential is needed to produce a given current, and that over potential may be regarded as the polarization over potential. Now, consider a simple reaction. Okay, consider a simple reaction, that is M Z plus giving after giving Z electrons, it is giving you M. Now, this is your Nernst relation. Okay, E is equal to E0 bar plus RT by ZF ln A. So, when using a large excess of support electrolyte, as I told you that key ingredient for these experiments, you need that is background electrolyte or support electrolyte. The mean activity coefficient stays approximately constant, because your ionic strength is huge. Therefore, any little change in concentration of your reactant does not alter the ionic strength a lot, and as a result of which the mean activity coefficient of the ions involved in this reaction remains approximately constant. So, you can write this expression is equal to E0 bar RT by ZF ln gamma, gamma into concentration. So, you can write in this way, and if you write these two together, so you write E0 plus RT by ZF ln C. Okay, so what is happening, that as I initially the ion concentration, the ion concentration at outer Helmholtz plane decreases to some value due to reaction. Okay. Okay. So, it was C, now it has decreased to some value, okay, C prime, and due to the reaction, as I told you, as I have shown to you, that like this, okay, with distance. So, this is your bulk concentration, okay, this is your bulk concentration, and this is your maybe concentration at the electrode, because concentration at the electrode is always 0, because electrolysis is occurring, reaction is taking place at the electrode. Therefore, your E is now converted to E prime because of the change in concentration. So, this you see this has changed, and this is your outer Helmholtz plane, this is your bulk solution, this is your electrode. So, electrodes, this value has reduced to some value because of this reaction. Okay. Actually, it should be reduced to at the electrode it should be 0, but suppose if it is reduced to here, then your E prime becomes, E becomes E prime. So, E prime is equal to E naught plus RT by ZF ln C prime. So, your corresponding potential is this. So, what is the concentration over potential because of this concentration gradient that is set up because of this reaction, you see. So, eta C, this is the concentration over potential. As I told you, because of this concentration polarization, a large over potential is needed to produce a given current. So, polarization over potential is eta C, and that can be related this way, E primed minus E, which is nothing but RT by ZF ln C primed by C. Okay. So, therefore, this is your this is the over potential that can be that can be calculated in this way. Next is thickness of the Nernst diffusion layer. And this is your Nernst diffusion layer. This is your bulk solution. This is your electrode. So, diffusion layer is typically of the order of 0.1 millimeter and depends very much on the condition of hydrodynamic flow, like stirring and convection. So, these are the means if you start the solution, then it's this thickness will be different. Okay. And this Nernst diffusion layer, it is not, it should not be confused with electrical double layer. Actually, electrical double layer is even less than a nanometer. If you if you maybe molecular atomic diameter thickness, I mean less than a nanometer. Now, the concentration gradient through the Nernst diffusion layer, through the Nernst diffusion layer, delta is the thickness. So, your this dc dx is the concentration gradient, is nothing but the difference in concentration, that is bulk minus that at the electrode divided by delta. This concentration gradient provides a flux of ions to the electrode, okay, through your J is proportional to this dc dx, okay, and of course, this is the diffusion coefficient. So, particle flux towards the electrode is given by this, J is d into this, which I already have told that this particle flux will be dependent on how, means the process is rate limited by the diffusion of the substances, I mean the diffusion of the ions, and this particle flux can be expressed in this way. Okay. Now, the cathodic current density towards the electrode is given by the product of particle flux and the charge transferred per mole of ion, that is Z into F. So, therefore, cathodic current density it is given by J is equal to Z F J. J is this particle flux, and the charge transferred is Z into F. So, basically it becomes Z F D C minus C prime divided by delta. Okay. The minimum rate of diffusion across the Nernst layer. Okay. So, minimum rate J min will be when C primed is, I mean maximum rate, not the minimum, because it will be maximum. Like if you think of this one, like it was C primed and it is 0. So, therefore, your gradient is more, this is your bulk, Okay. So, this gradient is less, this gradient is more, that is why this limiting current J limit, it is not the minimum, sorry. So, limiting current will be given by, you know, just you put C prime equal to 0. So, Z F J, which is equal to Z F D into C divided by delta, that is the limiting current. So, maximum rate of diffusion across the Nernst layer, okay, this layer delta. Okay. Now, using the Nernst Einstein equation, that is D equal to RT lambda divided by ZF square, your limiting current can be, you know, related, means if you just plug in this over here, okay, and where you know, lambda is the ionic conductivity. So, from the limiting current, I mean limiting current can be, you know, ultimately related to the Nernst, you know, Einstein equation. I mean you can replace D with this expression. So, this is the expression for the limiting expression for the limiting current. Okay. Now, as I told you, experimental technique on in which, I mean, I already have talked about this potential step voltammetry. Another method is your LSV, linear sweep voltammetry. Okay. So, linear sweep voltammetry, it is you know, at low potential value, the cathodic current is due to the migration of ions in the solution, and cathodic current grows as the potential reaches the reduction potential of the reducible species. Okay. And you know, as I told you, based on the previous equation, limiting current is ZFDC divided by delta, the maximum current is proportional to the molar concentration of the species. Okay. So, using this expression, using the linear, I mean the limiting current, you can find out the concentration of the species. So, this is an application of this measurement. Now, in potential you know, linear sweep voltammetry, you know, it is your potential is linearly swept. Okay. Linearly swept, I mean it is increased from, not like just like your potential step like this, it is linearly swept. So, having some value, then it is linearly increased with time, and you measure the current potential, you know. Okay. Now, next is there is another thing which is called the differential pulse voltammetry. So, I will come to linear sweep voltammetry, but before that let us have an idea of the differential pulse voltammetry. Okay. What is done here, the current is monitored before and after a pulse of potential is applied. Okay. A pulse of potential is applied and you monitor the current. Okay. So, and the output is the slope of a curve like obtained by linear sweep voltammetry. Okay. So, so this is your basically potential versus time, and this is your current as a function of time. Okay. And differential current versus differential potential is has got a plot like this. So, differential pulse voltammetry, in this case current is monitored before and after a pulse of potential is applied, and the curve is like this. So, now let us come to linear sweep voltammetry. As I told you that voltage is linearly swept from one value to another for some interval of time. Okay, for some interval of time. So, let us see, in linear sweep voltammetry fixed potential range is employed. So, this is your potential range, say V1 and V2. In other case, that is you know pulse potential step voltammetry, that is this one, it is just like a step function, but here what is happening, that it is very steep, I mean just like a vertical on this line, but here it has got some slope, slowly it is increased. So, it is like a potential step measurement, but it is a slanting one. Okay. Now, here in LSV, linear sweep voltammetry, the voltage is scanned from a lower limit to an upper limit as shown here. So, you see here lower limit and upper limit. Okay. So, V1 to V2 slowly increased. Okay. Scanned, it is a voltage is scanned. The voltage scan rate V is calculated from the slope of the line, okay, because difference divided by time means how much voltage it has increased to, maybe say 2 units and say in 2 seconds. So, 2 by 2 it is a 1. So, scan rate is 1 volt per say minute. Clearly, by changing the time taken to sweep the range will alter the scan rate. So, there is an option for changing the scan rate, and that scan rate may have some relation to the rate of electron transfer at the electrode. I mean, if it is swept very fast, then one situation may happen, or if it is swept very slowly. So, scan rate looks like that scan rate should have some relation. Okay. Now, thing is, the characteristics of linear sweep voltammogram recorded depends on the number of factors. Okay. So, you draw the current potential diagram, that is the voltammogram, and that has got characteristic is very much dependent on several factors. One is the rate of electron transfer. Okay. I mean, rate of electron transfer, I mean, you are here, I mean, you are doing this experiment, that is the electron transfer at the electrode, you are looking at, you are monitoring some electron transfer reaction. So, rate of electron transfer, okay, voltammogram will depend on the rate of electron transfer. Then chemical reactivity of the electroactive species, if it is a highly reactive species. Okay. So, chemical reactivity is a factor on which this voltammogram, I mean LS voltammogram will depend. Okay. And of course, the voltage scan rate. Okay. Now, in LSV, what you plot, that is current response, is plotted as a function of voltage, okay, rather than time, unlike potential step measurement. In potential step measurement, what you measure, you suddenly or instantaneously you change the potential voltage, you change, and then you measure the current response with time. Okay. You measure the current response, but here you do not do in that way, like you do not do any time, as you do not do any measurement as a function of time. What you do, you change the scan rate. So, scan rate change means that has some dependence on time. Okay. So, you change scan rate, but you plot the current response as a function of the voltage. Okay. So, you are changing the voltage. So, voltage change and then current response, you do it. Okay. So, in a linear sweep voltammetry you do that. Now typical plot is like this. Here linear sweep voltammogram, this is your potential versus time, and it is your you change the scan rate. Okay. So, potential you voltage increasing your scan rate, you do it. Okay. So, so what is happening, that this is as a result of change of scan rate. So, what is happening, that let us draw like one thing, you have got say this V1 V2. So, you change like this. Okay. You change like this. So, accordingly you will generate V1 to V2. Okay. So, your voltage here V1 is V2. V1 V2, V1 is V2. Okay. So, something like this, then maybe like this. It is because of the scan rate changing. Okay. So, peak potential, actually this peak should not change, this peak should not change. So, this is your peak potential EP C, cathodic peak potential. So, this peak potential changes, but its position should not change. So, this is as a result of change of scan rate, you get different response, current response, different current response. Okay. So, it depends on the so therefore, your profile, this current potential profile, current voltage profile, okay, it depends very much. So, you see here like changing, it is changing. So therefore, this is basically what you get. So rate of electron transfer rate, I mean electron transfer reactions, and then chemical reactivity of the electroactive species, and of course the voltage scan rate. Okay. Anyway, so this is pretty much what is done in your linear sweep voltammetry. So, you keep on changing the scan rate, okay, and you get different response curve. Okay. So, and from this you can get cathodic peak potential. Okay. Cathodic peak potential you will be getting, that is from this peak value. Okay. Next is now next is in your linear sweep voltammetry, next one question is remaining, that as I told you that the profile is dependent on the rate of electron transfer reaction. I mean, how fast this electron transfer reaction is occurring, and that is, it depends on the electron transfer rate. Okay. So, one question is still remaining, that if electron transfer processes are slow, okay, I mean slow in comparison to your voltage scan rate, slow compared to voltage scan rate, okay. And in that case, this is termed as quasi reversible, or maybe it is termed as irreversible, maybe irreversible electron transfer. Okay. Quasi reversible electron transfer. Okay. So in that case, if it is slow compared to the voltage scan rate, so let us have a plot, have a representative plot. In one case it is like this, maybe in another case it is like this, or maybe in still another case it is like this. So in this way, so slower and slower. So it is current and voltage. So this is electron transfer electron transfer process is slower, then it is shifting this way. Okay. So, that means it will give you the idea of whether the process is reversible or irreversible, I mean quasi reversible. So, you change the scan rate, and if you get a curve like this one, which if you get a curve like this one, no change. In one case this peak potential is not changing, in this case your peak potential is changing. So, that will give you the idea of whether it is a your electron transfer process is slower than your voltage scan rate, that is whether it is a quasi reversible or irreversible electron transfer. Okay. So, a slight modification of this has been done with cyclic voltammetry. Okay. In linear sweep voltammetry, voltage is swept from say V1 to V2, and it is kept for the value from V1 to V2, it is just done like that. But now if you do an arrangement such that you can change the voltage sweep from here to this value, and then it is coming back to its original value. So, cyclically change from say V1 to V2 and then V2 to again V1. Okay. So, this is your potential value and this is your time. Okay. So, in that case what do you expect? You expect a reversal of things, reverse curve. So, what is a typical graph for this? A typical graph could be like this is your current potential diagram. Okay. So, maybe something like this. Okay. So, this may be the curve will be joined by a line. Okay. Okay. So, this is your current and voltage. Okay. So, this is your cathodic EPC, and this is EPA, I mean E value corresponding to the peak position, and I, this is your I P C, and this is your IPA. Okay, these are the characteristic things that you can think of. So, this is your V2, so this is your V1. Okay, so means what is the usefulness of such a plot? So, now next the important thing is that we can determine the redox potential of a electroactive substance, of a redox couple, and it reflects the underlying kinetics. As I told you, in linear sweep voltammetry, changing of your scan rate gives you an idea of whether your electron transfer reaction is slow or fast. Now, in cyclic voltammetry is very similar to LSB, as I told you. In this case, voltage is swept between two values. Okay. So, so from one value to another at fixed rate. Okay. And however, now when voltage reaches V2 here, V2, okay, then again it is reversed, that is scan is reversed to V1 and the voltage is swept back to V1 value. A typical voltammogram recorded for reversible single electrode transfer reaction is here, it is shown here. Again the solution contains only one electrochemical reactant, that is very important. Now, your forward sweep produces an identical response to that is seen in linear sweep voltammetry, because from V1 to V2 is basically you are a linear sweep, you are drawing a linear sweep voltammogram. Okay. So if you just forget about this part, okay, you just forget about this, it looks like a linear sweep voltammogram. Okay. So when the scan is reversed, we simply move back through the equilibrium position, gradually converting the electrolysis product. So whatever reaction has taken place in this direction, it is reversed, okay, through the equilibrium position, gradually converting electrolysis products. The current flow is now from the solution species back to the electrode. So here electrode to solution, now here solution to the electrode, okay, back to the electrode. So occurs the opposite sense sense to the forward sweep, but otherwise behavior can be explained in an identical manner. So it is just the reverse, okay. For a reversible electrochemical reaction, CV, when it is recorded, will have well defined characteristics. As I told you that for a perfect reversible one, from the discussion of your linear sweep voltammeter, as I told you, this peak position is changing if it is not a reversible one, if it is a quasi reversible, okay. But if it is a reversible, then you should expect something like this, okay. Now what are those characteristics? Okay, characteristics are like the voltage separation between the current peaks EPA and EPC, this one, okay. The position of the peak, these are the characteristics. So position of the peak voltage do not alter as a function of voltage scan rate for this perfectly reversible one, okay. The ratio of the peak current is equal to the 1, this peak current, and that peak current. So this ratio is 1, okay. I mean this peak current IPC and IAC, these are equal to 1. The peak currents are proportional to the square root of the scan rate, okay. So these are important characteristics of your and the voltage separation is given by EP A and EPC now, and the ratio of the peak current is equal to 1. The peak currents are proportional to the square root of scan rate, okay. So this peak currents are proportional, I mean this peak currents, okay, is proportional to the square root of the scan rate. So when scan rate is more, your peak current is more, like that, but of course it is in a square root fashion. But one point which I should tell you, that if it is a quasi reversible situation, then your cyclic voltammogram, I mean if you change, do like this, then your this voltammogram will change something like this, and it may not look, may not end up like this, okay. Here you see this, it is just like a perfect hysteresis kind of thing, but that may not be observed, okay. So that is a signature of your irreversibility, okay. So these are the points that one should carefully look into while considering your this current potential diagram for this voltammetric studies. So what we have learned out of this discussion, I mean this kinetics, about the kinetics of electrode. Now we have here in this particular piece of lecture, we talked about mainly this voltammetry, various techniques, various voltammetric techniques like potential step voltammetry, LSV, and cyclic voltammetry. Okay. Now in potential step voltammetry you can find out, of course, the diffusion coefficient of the ions to the electrode. So and it is diffusion limited. I mean, sometime when first layer of reactants are used up, or second layer, then the reactants are to be taken from a distance place towards the electrode. So that is limited by the diffusion. Now this voltammetry has got advantages, like you can find out the concentration, you can find out the electrode potential, okay, and also you can find out, I mean, you can know about, you can get information about the reversibility of the process, I mean, whether this electron transfer rate is reversible or not, by changing your scan rate, okay. And this characteristic cathodic peak potential, anodic peak potential, and also peak current, these are very characteristic of some electroactive substance, okay. So from this, I mean, you can know more about the electron transfer process, that is, I mean, electron transfer process that is occurring at the electrode, I mean, electroactive substances. You can find out concentration. So these are the these are the advantages or applications, I mean, with respect to using your voltammetric determinations, okay. So that's all for today's discussion. So thank you for your patience.